Every planet in our solar system spins. Most of them spin in roughly the same upright fashion, tilted just a few degrees off vertical, like tops that wobble only slightly. But one planet breaks this pattern so violently that the first time astronomers measured its orientation, they had to check their instruments. Uranus doesn't tilt a little. It doesn't lean modestly like Earth or Saturn. Uranus is lying almost completely on its side, rolling around the sun like a ball instead of spinning like a top. Its north pole sometimes points almost directly at the sun, while its south pole faces the cold emptiness of deep space. Something did this. Something enormous. And tonight, we're gonna figure out what could knock an entire planet sideways, and why the answer is stranger than you might expect. Before we dive in, if you find this kind of deep space exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you probably learned in school, but never thought too deeply about. Every planet in our solar system rotates on an axis. You can think of that axis as an invisible line running straight through the planet from the North Pole to the South Pole. The planet spins around this line the same way a basketball spins on a finger. For most planets, this axis of rotation is roughly vertical relative to the flat plane in which the planet orbits the sun. We call that flat plane the ecliptic, and the angle between a planet's rotation axis and a line perpendicular to the ecliptic is what astronomers call axial tilt, sometimes referred to as obliquity. If a planet had 0 degrees of axial tilt, it would spin perfectly upright, like a top standing straight on a table. Its north pole would point directly upward relative to its orbit, and its equator would line up precisely with its orbital plane. There would be no seasons on such a world because every latitude would receive the same amount of sunlight all year round. The sun would trace the exact same arc across the sky every single day, never climbing higher, never dipping lower, unchanging from one month to the next. There would be no summer, no winter, no shift in the length of the day. Just the same steady sunlight, day after day, year after year, forever. Earth doesn't have 0 tilt. Earth's axis is tilted about 23.5 degrees from vertical. That lean is the reason we have seasons. This is something that most people learn in school, but very few people fully appreciate. When the Earth's north pole is tilted toward the sun, the northern hemisphere receives more direct sunlight. The sun climbs higher in the sky. Days grow longer. The energy hitting each square meter of ground is greater because the sunlight arrives at a steeper angle, concentrating rather than spreading. That's summer. 6 months later, when the North Pole tilts away from the sun, the reverse happens. The sun stays lower in the sky. Days become shorter. Sunlight hits the ground at a shallower angle and spreads out over a larger area, delivering less energy per square meter. That's winter. The seasons aren't caused by Earth being closer to or farther from the sun. In fact, Earth is actually slightly closer to the sun during the northern hemisphere's winter than during its summer. The seasons are entirely about tilt, about the angle at which sunlight strikes the surface, and 23.5 degrees is a fairly moderate lean. It's enough to give us distinct seasons, warm summers, cold winters, mild springs, and pleasant autumns, but it's not so extreme that any part of Earth outside the polar regions is plunged into months of total darkness, or months of unbroken daylight. It's a gentle tilt, a comfortable tilt. A tilt that, as it turns out, has been remarkably favourable for the development and survival of life. Now, here's the important thing. Most planets in our solar system have relatively modest axial tilts. They lean a little, but not dramatically. And this makes perfect sense when you understand how planets form in the first place. The solar system began as a vast, spinning cloud of gas and dust called the solar nebula. About 4.6 billion years ago, this cloud started collapsing under its own gravity. As it collapsed, it flattened into a disk, the same way a ball of pizza dough flattens when you spin it. The sun formed at the dense, hot center. The planets formed within the disk, building themselves up piece by piece as dust grains stuck together into pebbles. Pebbles clumped into boulders. Boulders accumulated into protoplanets. And protoplanets grew into full planets through collisions and gravitational attraction. Because everything in the disk was rotating in roughly the same direction and roughly the same plane, the planets that formed within it naturally ended up spinning in roughly that same direction as well, with their axes pointing roughly perpendicular to the disk. There's a term for this: prograde rotation. It means the planet spins in the same direction it orbits the sun, with its axis roughly aligned with the overall angular momentum of the solar system. This is what the physics predicts. It's the default outcome, the expected baseline, the natural result of forming inside a spinning disk. Let me take you through each planet so you can see just how consistent this pattern is, and just how violently Uranus breaks it. Mercury has an axial tilt of practically 0. It's about 0.03 of a degree. Mercury spins almost perfectly upright relative to its orbit. This makes sense for a small, dense planet sitting close to the sun, where tidal forces from the sun's gravity have had billions of years to gradually align its rotation with its orbit. Mercury barely tilts at all. It's about as upright as a planet can get. Venus is a special case, and we'll come back to it in a moment because it has its own strange story to tell. But for now, let's set it aside and continue down the line. Earth, as I mentioned, tilts at about 23.5 degrees, a moderate lean, significant enough to create vivid seasons, but well within the range of what planetary formation models predict. Nothing surprising, nothing alarming, just a slight lean that happens to make our world habitable and beautiful in its seasonal variety. Mars tilts at about 25.2 degrees. That's remarkably similar to Earth's tilt, and it means Mars has seasons too, though they're roughly twice as long because Mars takes about 687 Earth days to complete one orbit around the Sun. The temperatures are far more extreme than anything on Earth because Mars has almost no atmosphere to moderate them, but the basic seasonal cycle would feel broadly familiar. Warmer summers, cooler winters, same mechanism as Earth seasons, axial tilt. Jupiter, the largest planet in the solar system, a world so massive it contains more mass than all the other planets combined. Tilts at only about 3.1 degrees. Jupiter is almost perfectly upright. This is exactly what you'd expect from a massive gas giant that formed directly from the solar nebula. Jupiter was so large and so gravitationally dominant that very little could have disturbed its spin axis after formation. It's spinning almost exactly the way the original swirling cloud of material was spinning when the planet first coalesced. Steady, stable, undisturbed. Saturn tilts at about 26.7 degrees, similar to Earth and Mars. Saturn's tilt may have been influenced by long-term gravitational interactions with Neptune over the age of the solar system, a mechanism we'll explore later. But the key point is that Saturn's tilt, while noticeable, is still within a range that doesn't demand a catastrophic explanation. It's a modest lean, a manageable lean. Nothing that keeps planetary scientists awake at night, wondering what went wrong. Neptune tilts at about 28.3 degrees, again, comfortably in the same neighborhood as Earth, Mars, and Saturn. Neptune leans a bit, but nothing extreme, nothing alarming, well within normal parameters. Do you see the pattern? Mercury is almost perfectly upright. Jupiter is almost perfectly upright. Earth, Mars, Saturn, and Neptune all tilt between roughly 23 and 28 degrees. There's a fairly narrow range here. The rocky planets and the gas giants alike cluster around either very small tilts or moderate tilts in the low to mid-20s. This is exactly consistent with what we'd expect from a solar system that formed from a single rotating disk of material. Some gravitational nudges over billions of years have shifted the tilts a few degrees here and there, but nothing wild, nothing extreme. Everything makes sense. And then there's Uranus. Uranus has an axial tilt of about 97.8 degrees. Let me say that again because it's genuinely one of the most startling numbers in all of planetary science. 97.8 degrees. That's not a modest lean. That's not even a dramatic lean. That is a planet lying almost completely on its side. Uranus rotates with its axis nearly parallel to the plane of its orbit, nearly perpendicular to every other planet in the solar system. Try to picture this. Imagine a spinning top on a table, standing upright, its axis pointing straight at the ceiling. That's roughly how most planets spin. Now imagine picking up that top and pushing it over, almost all the way over, until the axis that used to point at the ceiling is now pointing at the wall. Not up, not down, sideways, nearly horizontal. That's Uranus. Its rotation axis doesn't point up or down relative to its orbit. It points almost directly sideways. When Uranus orbits the Sun, it doesn't spin upright like the other planets do. It effectively rolls along its orbital path like a ball rolling along the floor. And this creates a genuinely bizarre situation. There are times during Uranus's 84-year orbit when its north pole points almost directly at the Sun. For roughly 21 years, the northern hemisphere basks in continuous sunlight, while the southern hemisphere sits in continuous darkness. Then, a quarter of an orbit later, the Sun shines on the equator, and both hemispheres get relatively equal illumination. Another quarter of the orbit, and the situation reverses. The South Pole faces the Sun for another 21 years, while the North Pole is plunged into 2 decades of darkness. This is profoundly strange, and it was recognized as profoundly strange from the moment astronomers first understood Uranus's true orientation. Because nothing about the standard model of solar system formation produces a tilt this extreme. The solar nebula hypothesis predicts roughly upright rotation. You can get small tilts from minor gravitational perturbations. You can get moderate tilts of 20 or even 30 degrees from various dynamical processes acting over billions of years. But 98 degrees? That doesn't just happen through the gentle, gradual processes that shaped most of the solar system. Something intervened. Something powerful. Now, let me come back to Venus. Because I promised we would, and because Venus helps clarify exactly what makes Uranus's situation so puzzling. Venus has an axial tilt of about 177.4 degrees. That number sounds even more extreme than Uranus, and in a sense, it is. Venus is essentially upside down. Its rotation is retrograde, meaning it spins in the opposite direction from its orbit. But here's why Venus's situation is fundamentally different from the puzzle of Uranus. Venus rotates incredibly slowly. One full rotation takes about 243 Earth days, actually longer than its year of about 225 Earth days. This extreme slowness is the critical clue. It suggests that Venus's rotation has been heavily modified by tidal interactions with the Sun and possibly by friction between its extraordinarily thick atmosphere and its solid surface. Over billions of years, these forces could have gradually slowed its rotation, brought it nearly to a halt, and allowed it to settle into a slow retrograde spin. Venus may have been slowly braked and gently flipped by steady tidal influence, not knocked over by a single dramatic event. Uranus is completely different. Uranus rotates relatively quickly. One rotation takes only about 17 hours and 14 minutes. That's actually faster than Earth's 24-hour day. This tells us immediately that Uranus hasn't been tidally braked the way Venus likely was. Whatever tilted Uranus didn't slow it down. The planet is still spinning vigorously. It's just spinning sideways. And Uranus sits far from the Sun, about 19.2 times Earth's distance. Out there, the Sun's tidal forces are negligible. The Sun's gravity simply cannot reach across that immense gulf of space and slowly twist Uranus's axis the way it could with Venus, which orbits much closer. Whatever tilted Uranus, it wasn't a slow, gentle, tidal process. It was something else entirely. Something far more dramatic. Let's go back to how Uranus was discovered, because the story itself reveals something about how full of surprises this planet turned out to be. Uranus was the first planet ever discovered with a telescope. Mercury, Venus, Mars, Jupiter, and Saturn are all bright enough to see with the naked eye, and they've been known to every human civilization that ever looked at the sky. The ancient Babylonians track them. The Greeks name them after gods. For thousands of years, humanity assumed the solar system had exactly 6 planets, including Earth, and that this was the complete inventory. Nobody expected a 7th. On March 13th, 1781, a German-born British astronomer named William Herschel was surveying the night sky with a telescope he had built himself in the garden of his house in Bath, England. Herschel was a meticulous observer. He spent countless nights systematically scanning the sky, cataloguing stars and nebulae. On this particular night, he noticed something that didn't look quite right. One object in the constellation Taurus wasn't a sharp point of light like a star. It appeared as a tiny disk, soft-edged, slightly fuzzy. At first, Herschel thought he'd found a comet. He reported it as such to the Royal Society, but as other astronomers tracked the object over the following weeks and months, calculating and refining its orbit, they realized it wasn't a comet at all. It was moving in a nearly circular path far beyond Saturn, out in the cold, dark reaches of the outer solar system. It was a new planet, the first planet discovered in recorded history. The solar system, which humanity had assumed contained 6 worlds for millennia, suddenly contained 7. Herschel wanted to name the new planet after King George III of England, but the international community eventually settled on Uranus, after the ancient Greek god of the sky. The discovery was revolutionary. It proved that the solar system was larger and more complex than anyone had assumed. If there was one undiscovered planet lurking beyond Saturn, could there be more? This question eventually led to the discoveries of Neptune in 1846, and later Pluto in 1930, and it transformed how humanity thought about the extent and complexity of our cosmic neighborhood. But it took decades after the discovery to understand just how strange Uranus truly is. In the years and decades following 1781, astronomers worked to determine the planet's basic physical properties, its distance from the Sun, its orbital period, about 84 Earth years, its size, roughly 4 times Earth diameter, and eventually the orientation of its rotation axis. This last measurement was the one that created the deepest puzzle. As astronomers studied Uranus's moons, they noticed something peculiar. The moons didn't orbit in the plane of the solar system the way most planetary moons do. Instead, they orbited around Uranus's equator, which was tilted nearly 90 degrees from the plane in which the planets orbit the Sun. This was the first strong evidence that Uranus's entire rotational system, the planet, its moons, and eventually its rings, was all tilted sideways together. Let me explain why the moons matter here. Because this is a critical piece of the puzzle that constrains every theory about the tilt. When a giant planet forms, it often generates a disk of material around itself, a miniature version of the solar nebula. Moons form from this circumplanetary disk, condensing and accreting in the same way that planets form from the larger disk around the Sun. Because this smaller disk is centered on the planet's equator, the moons that form within it end up orbiting in the planet's equatorial plane. This is exactly what we see with Jupiter's 4 large Galilean moons. They orbit very close to Jupiter's equatorial plane. Saturn's major moons follow the same pattern. Moons form in the equatorial disk, and they stay there. Uranus's 5 major moons do the same thing. Miranda, Ariel, Umbriel, Titania, and Oberon all orbit in Uranus's equatorial plane. Their orbits are nearly circular, well-ordered, and prograde, meaning they orbit in the same direction Uranus spins. But because Uranus itself is tilted 98 degrees, its equatorial plane is nearly perpendicular to its orbit around the Sun. The moons orbit sideways relative to the rest of the solar system. They're not following the ecliptic, they're following Uranus's tilted equator. This tells us something incredibly important. Whatever tilted Uranus either happened very early, before the moons finished forming, so that the circumplanetary disk was already tilted and the moons formed in the new plane, or it happened in a way that tilted the entire system simultaneously, planet and surrounding disk and proto-moons all together. Either way, the tilt isn't superficial. It's not just the planet's outer atmosphere that got shoved sideways. The whole Uranian system, planet, moons, and all, is tilted as one coherent unit. Uranus has 28 known moons in total. Most are small, irregular objects, likely captured from the surrounding debris during the chaotic early solar system. But the 5 major moons are spherical, substantial worlds, each clearly formed from a disk around the planet. Their orderly, circular, equatorial orbits are powerful evidence that whatever caused the tilt happened either before these moons formed or during their formation, when the disk material could still adjust to a new orientation and settle into a new equatorial plane. Uranus also has a system of 13 known rings. These rings are thin, dark, and difficult to observe, nothing like Saturn's magnificent bright rings of ice. Uranus's rings are made of dark particles, possibly containing radiation-darkened organic compounds, and they were only discovered in 1977 when astronomers observed them blocking the light of a background star as Uranus passed in front of it. Like the moons, the rings orbit in Uranus's equatorial plane. They're tilted sideways too. Every component of the Uranian system has been rotated together. When Voyager 2 flew past Uranus in January of 1986, it provided humanity's first, and so far only close-up look at this sideways world. The spacecraft confirmed the extreme tilt and measured it precisely. It photographed the moons and rings in detail. It measured the planet's magnetic field, which turned out to be tilted in yet another bizarre direction, something deeply significant that we'll explore later. And it sent back images of a planet that looked eerily featureless, a pale blue-green sphere with almost no visible cloud patterns or storm structures, in stark contrast to the churning, swirling atmospheres of Jupiter and Saturn. Voyager 2's flyby lasted only about 6 hours at close range. The spacecraft was moving at roughly 42,000 miles per hour relative to Uranus, and couldn't slow down. It swept past, collected as much data as its instruments could gather, and continued onward toward Neptune. But even in those few hours, it confirmed beyond any doubt what astronomers had long suspected from ground-based observations. Uranus is genuinely, physically, completely tilted on its side. This wasn't an artifact of measurement uncertainty. It wasn't an optical illusion. It was real. The planet was sideways, its moons were sideways, its rings were sideways, and its magnetic field was tilted in an entirely different direction that made the whole situation even more confusing. So why can't the solar nebula model explain this tilt on its own? Let me walk through the physics carefully, because understanding this is essential to understanding why the tilt demands a special explanation. When the solar system formed 4.6 billion years ago, the solar nebula was a vast rotating disk. A fundamental law of physics called conservation of angular momentum governs what happens in a rotating system. Angular momentum is essentially a measure of how much rotational motion an object has. It depends on mass, velocity, and distance from the axis of rotation. And it is conserved, meaning it can be transferred from one object to another, but it can't be created or destroyed without an external force. As material in the disk collapsed to form each planet, that planet inherited the angular momentum of all the material it accumulated. Because all the material in the disk was rotating in roughly the same direction and roughly the same plane, the growing planet naturally ended up spinning in that same direction, with its rotation axis pointing roughly perpendicular to the disk. There's some room for random variation. As a planet grows, it accumulates material from slightly different parts of the disk. Some chunks arrive at slight angles, delivering angular momentum in directions that aren't perfectly aligned with the planet's existing spin. Random impacts during the final stages of planetary accretion can also nudge the axis a few degrees one way or another, or computer simulations of planet formation confirm this picture. They show that you can easily produce tilts of a few degrees just from the random accumulation process. You can even get tilts of 10 or 15 degrees without anything unusual happening. But those same simulations almost never produce tilts anywhere near 98 degrees through accretion alone. Getting to 98 degrees requires a special intervention, a source of angular momentum delivered in a very specific direction, far beyond what random accumulation provides. That's the situation with Uranus. The normal process of planetary formation can account for small tilts. It can even account for moderate tilts if you allow for some gravitational perturbations over billions of years. But 98 degrees is wildly outside the range of anything the standard formation model produces on its own. The rotation axis wasn't gently nudged off course, It was wrenched nearly perpendicular to where physics says it should be. Something extraordinary happened, and this is what makes Uranus one of the most important puzzles in all of planetary science. It's not merely a curiosity or a cosmic footnote, it's a direct challenge to our understanding of how the solar system formed and evolved. If we can explain why Uranus is tilted, we learn something fundamental about the kinds of events and forces that shaped our solar system during its youth. If we can't explain it, we're missing something critical about how planets form, how they interact gravitationally, and what kinds of catastrophic or gradual processes can reshape an entire world long after its initial formation. The mystery deepens considerably when you consider the broader context of the early outer solar system. The region where Jupiter, Saturn, Uranus, and Neptune orbit today was not always the orderly, stable place it appears to be. Computer models of the solar system's early evolution, developed over the past few decades and tested against observations of the current orbits and compositions of the planets, suggest that the giant planets originally formed closer together and closer to the Sun than they are now. Over the first few 100 million years after their formation, they migrated outward, pushed and pulled by gravitational interactions with each other, and with the vast disk of rocky and icy debris that still surrounded the young Sun. During this migration, the giant planets pass through orbital resonances, special configurations where their orbital periods aligned in simple mathematical ratios, like 2:1 or 3:2. When two planets are in resonance, their gravitational influence on each other becomes amplified. They tug on each other at the same point in their orbits over and over again, building up the effect. These resonances can destabilize orbits and cause sudden, dramatic changes. In some models, the instability triggered by these resonances was genuinely violent. Planets swapped positions. Orbits that had been nearly circular became highly elongated. Some models even suggest the early solar system may have contained a fifth giant planet, a world comparable in size to Uranus or Neptune that was flung entirely out of the solar system by gravitational interactions with the others, ejected into interstellar space, wandering alone in the darkness between the stars forever. This era of chaos, sometimes called the giant planet instability, or more specifically in some formulations, the Nice model after the city in France, where it was first developed, likely lasted tens of millions of years. And it's during this period, this epoch of orbital reshuffling and gravitational violence, that whatever happened to Uranus most likely took place. The solar system was a dangerous, chaotic environment in its youth. Planets were migrating, orbits were shifting and crossing. Enormous gravitational forces were rearranging the architecture of the entire system. And somewhere in all that turmoil, something tipped Uranus nearly onto its side. But what exactly? What kind of event has enough energy, enough force, enough angular momentum to push a planet 14.5 times the mass of Earth to a tilt of 98 degrees? What can do that to a world roughly 51,000 kilometers across? A vast sphere of hydrogen, helium, water, ammonia, and methane ices? And how did the moons and rings survive the event or reform themselves afterward in such orderly, circular, equatorial orbits? These are the questions that planetary scientists have been working to answer for decades. And the answers, it turns out, are more complex and more fascinating than anyone originally imagined. The leading explanation involves a catastrophic collision, possibly the single most violent impact event in the recorded history of the outer solar system. But there are also alternative explanations that don't require a collision at all, explanations involving subtle gravitational forces acting patiently and steadily over millions of years, slowly tipping the planet degree by degree until it reached the extreme orientation we observe today. The truth might involve elements of both, or it might be something we haven't fully worked out yet. What we know for certain is that Uranus sits at nearly 98 degrees. Its moons orbit sideways. Its rings circle sideways. Its magnetic field is skewed in yet another unexpected direction. And the story of how all this came to be is one of the most compelling and consequential mysteries in our understanding of how our solar system became the place we call home. So something extraordinary happened to Uranus. Something powerful enough to take a planet 14.5 times the mass of Earth and shove its rotation axis from a roughly upright position to nearly 98 degrees. And for most of the past half century, the leading explanation has been beautifully simple in concept and staggeringly violent in execution. Something hit it, something enormous. This is called the giant impact hypothesis, and to understand why scientists have favored it for so long, you first need to appreciate just how common collisions were in the early solar system. Because the solar system you see today, with its neatly spaced planets orbiting in tidy ellipses, is not the solar system that existed 4.5 billion years ago. The young solar system was a demolition derby. It was chaos on a scale that's almost impossible to imagine. After the sun ignited at the center of the solar nebula, the remaining gas and dust in the disk began clumping together. Small grains stuck to each other and grew into pebbles. Pebbles accumulated into boulders. Boulders collided and merged into objects miles across, called planetesimals. And planetesimals slammed into each other at tremendous speeds to build protoplanets, objects the size of small planets, hundreds or even thousands of kilometers across. This entire process, from dust grain to planet, took roughly 10 to 100 million years. And throughout that entire period, collisions were the primary engine of growth. Planets didn't form gently. They were built through violence. The evidence for this violence is everywhere. Our own moon almost certainly formed from a giant impact. The leading theory for the moon's origin holds that about 4.5 billion years ago, a Mars-sized body now called the Ur struck the young Earth at a glancing angle. The collision was catastrophic. It vaporized vast amounts of rock from both bodies. The impact energy was so enormous that it partially melted the entire Earth. A disk of superheated debris was flung into orbit around our planet, and from that disk, the moon condensed. This isn't speculation. The impact hypothesis explains why the moon is made of material chemically similar to Earth's outer layers, why it has a relatively small iron core, and why isotopic ratios in Apollo lunar samples match predictions. The evidence is so strong that the giant impact origin for the moon is considered the standard model, the explanation that fits the data better than any alternative. Mercury's unusually large iron core, which makes up about 70% of the planet's mass, is also thought to be the result of a giant impact. Early in Mercury's history, a massive collision may have stripped away most of its rocky outer layers, leaving behind the dense metallic core surrounded by only a thin mantle of rock. Mars's dramatic hemispheric dichotomy, where the northern hemisphere is smooth and low-lying, while the southern hemisphere is rough and elevated, may also be the scar of an ancient impact so large it reshaped the entire planet. Venus's slow retrograde rotation, which we discussed earlier, might have been influenced by a large impact as well, though tidal effects from the sun are the more commonly favored explanation. The point is that giant impacts were not rare events in the early solar system. They were routine. They shaped every rocky planet. And there's no reason to think the giant planets were immune. In fact, there's every reason to think they experienced impacts too. The outer solar system contained enormous amounts of material during the formation period. Tens of Earth masses worth of rocky and icy debris filled the region where the giant planets grew. The giant planets got big precisely by sweeping up this material. And the bigger they got, the stronger their gravity became, pulling in even more objects on collision courses. Now, with this context in mind, imagine the young Uranus. It has already formed as a massive ice giant, roughly 14.5 Earth masses of hydrogen, helium, water ice, methane ice, and ammonia ice, compressed into a sphere about 4 times the diameter of Earth. It's spinning in roughly the expected prograde direction, its axis pointing more or less perpendicular to its orbital plane, consistent with the angular momentum it inherited from the solar nebula. Around it, a disk of gas and debris is beginning to condense into moons. And then something hits it. The impactor in the simplest version of the hypothesis is an object between about 1 and 3 Earth masses. That might not sound like much compared to Uranus's total mass of 14.5 Earth masses, but 1 Earth mass is an enormous object. It's the body roughly the size of our entire planet. 3 Earth masses is an object larger than any rocky planet in the solar system today. These are not asteroids. These are not comets. These are protoplanets. Fully formed or nearly formed worlds in their own right, hundreds or thousands of kilometers across, hurtling through the young solar system on orbits that cross the path of other growing planets. When an object this massive strikes a giant planet at typical orbital velocities, which in the outer solar system would be on the order of several kilometers per second, the energy released is almost inconceivable. We're talking about energies that dwarf the combined nuclear arsenals of every nation on Earth by factors of billions. The collision wouldn't look like a rock hitting a wall. At these scales, both objects behave more like fluids than solids. The impactor would plunge into Uranus's outer atmosphere, drive deep into its gaseous and icy interior, and deposit its kinetic energy and angular momentum directly into the planet's bulk. And here's the key physics. Angular momentum is a vector. It has both a magnitude and a direction. When the impactor hits Uranus, it brings its own angular momentum, which depends on its mass, its velocity, and the angle at which it strikes. If the impactor arrives at a steep angle relative to Uranus's existing spin axis, the angular momentum it delivers can be oriented in a very different direction from Uranus's current spin. The result is that the planet's total angular momentum, the sum of its original spin, plus the angular momentum delivered by the impact, ends up pointing in a new direction. Think of it like a spinning top being struck from the side by a heavy ball. Before the collision, the top is spinning around a vertical axis. The ball arrives horizontally, carrying its own momentum. After the collision, the combined system has a new axis of rotation that's tilted away from the original vertical. The stronger the sideways hit, the more the axis shifts. For Uranus, the calculations show that a single impact from a body of 1 to 3 Earth masses, arriving at the right angle and the right speed, can deliver enough angular momentum to shift the rotation axis by roughly 90 degrees, The first serious computational studies of this scenario were performed in the late 1980s and early 1990s. Researchers used what are called smoothed particle hydrodynamic simulations, a technique where both the impactor and the target planet are modeled as collections of thousands or millions of tiny particles, each representing a chunk of material. The particles interact through gravity and pressure forces, and the simulation tracks how they move, collide, heat up, and redistribute after the impact. These early simulations were crude by modern standards. Computing power in the 1990s was limited, so the number of particles was small and the resolution was low. But even with those limitations, the results were striking. A single impactor of about 1 to 2 Earth masses, hitting Uranus at a speed of a few kilometers per second at the right angle, could tilt the planet to approximately 98 degrees. The impact was violent enough to completely reorganize Uranus's angular momentum vector, but not so violent that it destroyed the planet. Uranus survived the collision largely intact, just rotated. This result was exciting because it showed that the tilt was physically achievable through a single event. You didn't need to invoke anything exotic or unknown. Just a big rock hitting a big planet at the right angle. The physics was well understood. The scenario was consistent with what we know about the early solar system's violent formation period. And it explained the magnitude of the tilt in a straightforward way. But as with all good science, the simple version immediately ran into complications. And those complications centered on one of the most important constraints we discussed earlier: the moons. Remember, Uranus's 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, all orbit in the planet's equatorial plane. Their orbits are nearly circular and prograde. This means that whatever tilted Uranus also tilted the system that produced those moons. And this is where the physics becomes delicate, because a giant impact doesn't just tilt a planet, it also violently disrupts everything around it. If Uranus already had a disk of material orbiting its equator before the impact would have tilted the planet, but not necessarily the disk. Angular momentum is conserved for each component separately. The planet gets tilted because the impactor's angular momentum is added directly to the planet's spin. But the orbiting disk material, which is far from the impact site and doesn't directly absorb the impactor's momentum, would tend to stay in its original plane. You'd end up with a tilted planet surrounded by a disk that's still orbiting in the old, untilted plane. Over time, the disk would precess and eventually settle into the new equatorial plane through a process called viscous dissipation. But this takes time, and the details depend sensitively on the disk's mass, temperature, and thickness. This was a concern because the moon's orderly equatorial orbits suggest they formed from a disk that was already aligned with the tilted equator. One solution is that the impact happened before the moons formed. If the impact occurred while Uranus was still young, while the circumplanetary disk was still massive and hot and actively forming moons, then the disk could have had time to realign itself with the new equatorial plane before the moons condensed. The moons would then form in the tilted plane, producing the orderly equatorial orbits we observe today. Another possibility is that the impact itself generated a new disk. When a massive object plunges into a gas giant, enormous amounts of material can be ejected from the planet. Some of this material escapes into space, but some of it goes into orbit around the planet, forming a debris disk. If the impact was energetic enough to launch sufficient material into orbit, this new disk would naturally form in the planet's new equatorial plane. aligned with the tilted axis. Moons forming from this impact-generated disk would orbit in the tilted plane from the very start. Modern simulations, run on far more powerful computers with millions of particles and much higher resolution than the original 1990s studies, have explored both of these scenarios in detail. And they found that both are viable under certain conditions, but both also have constraints and challenges that make the full story more complicated than the simple headline of a single big impact. One of the most important developments came in the 2000s and 2010s, when researchers began exploring what's called the multiple impact hypothesis. Instead of one single cataclysmic collision, this scenario proposes that Uranus was tilted gradually through a series of smaller, but still very large impacts. Maybe it wasn't one object of 3 Earth masses. Maybe it was 2 or 3 objects each, around half an Earth mass to 1 Earth mass, arriving at different times over a span of several million years. Each impact would tilt the axis a few tens of degrees. After 2 or 3 such impacts arriving from roughly similar directions, the cumulative effect could reach 98 degrees without any single collision needing to be as extreme as the one-shot scenario requires. This is appealing for several reasons. First, smaller impactors are statistically more common than larger ones. In any population of planetesimals and protoplanets, there are always more small objects than big ones. The probability of Uranus being hit by 2 or 3 bodies of 1 Earth mass is actually higher than the probability of being hit by a single body of 3 Earth masses. Second, multiple smaller impacts are gentler on the Moon system. Each individual collision deposits less energy and disrupts the circumplanetary disk less violently. Between impacts, the disk has time to settle and re-equilibrate. Moons that have already started to form have a better chance of surviving each individual impact. By the time the tilt reaches its final value of 98 degrees, the Moon system has had time to adjust incrementally rather than being catastrophically disrupted all at once. However, the multiple impact scenario has its own challenges. The impacts need to come from roughly the same direction, or at least from directions that don't cancel each other out. If one impact tilts Uranus 30 degrees to the left, and the next tilts it 30 degrees to the right, the net effect is approximately 0. You need some degree of consistency in the impact geometry, and getting that from random collisions is a matter of probability. Simulations show that it's possible, but not guaranteed. Sometimes the random impacts reinforce each other. Sometimes they cancel out. The outcome depends on the specific details of each collision, the mass, velocity, and angle of each impactor. There's another critical constraint that any impact model has to satisfy: Uranus's internal heat, or more precisely, its striking lack of internal heat. Every giant planet in the solar system radiates more energy than it receives from the sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight. Saturn radiates about 1.8 times as much. Neptune radiates about 2.6 times as much. These planets are still slowly cooling from the heat of their formation billions of years ago. Their interiors are hot, and that heat gradually leaks out through their atmospheres, producing a detectable excess of infrared radiation. But Uranus is different. Uranus radiates almost no excess heat. The energy it emits is very close to the energy it receives from the sun, within the margins of our measurements. This means either Uranus's interior has already cooled down, which is unlikely given its size and composition, or something is preventing the interior heat from reaching the surface, and a giant impact could explain this. When a massive object strikes a planet, it deposits a tremendous amount of energy into the planet's interior. But the way that energy is distributed depends on the details of the collision. Some impact simulations show that a giant impact on Uranus could have created a stable thermal boundary layer deep inside the planet, a region where temperature changes sharply over a short distance. This boundary layer would act like an insulating blanket, trapping heat in the deep interior and preventing it from reaching the surface. The planet's core would remain hot, but the heat wouldn't be able to escape efficiently, making Uranus appear cold and thermally inactive from the outside. This is a genuinely powerful piece of evidence for the impact hypothesis, because it connects two seemingly unrelated observations: the extreme tilt and the anomalous lack of internal heat. If a single event, a giant collision, can explain both, that's a strong argument in its favor. Scientists are always looking for explanations that account for multiple observations simultaneously, rather than requiring separate explanations for each one. But not everyone is convinced that the thermal boundary layer story works perfectly. Some researchers have pointed out that the detailed thermal structure of Uranus's interior is still poorly understood. We have very limited data on what's happening deep inside the planet. Voyager 2's flyby in 1986 provided valuable data on the upper atmosphere and magnetic field, but it couldn't directly probe the deep interior. Without better measurements of Uranus's gravitational field, its atmospheric composition at depth, and its internal density structure, it's difficult to confirm or rule out the thermal boundary layer hypothesis. Let's talk about what happens during an impact simulation in more detail, because the physics is fascinating and it matters for understanding whether the moons could survive. In a typical simulation of a single large impact on Uranus, the impactor approaches the planet at a speed of several kilometers per second. It's a protoplanet, maybe 1.5 Earth masses of rock and ice compressed into a sphere roughly the size of Earth. It hits Uranus at an oblique angle, not head-on, but at a glancing trajectory. This is important because a perfectly head-on collision would drive straight into the planet's core without delivering much torque, much twisting force. To tilt the planet efficiently, the impact needs to be off-center, striking at an angle that maximizes the lever arm and thus the angular momentum transfer. In the first seconds of the collision, the impactor plows into Uranus's thick, gaseous envelope, generating a massive shockwave. Temperatures soar, material from both bodies is superheated and deformed. The impactor drives inward, shedding material and mixing its rocky and icy composition with Uranus's hydrogen-helium envelope. If the impact is glancing enough, the impactor's core may not reach Uranus's core. Some material is expelled into space, some goes into orbit around Uranus, forming a debris disk. Within the first few hours, the chaos begins to subside. The spin axis has shifted dramatically. Material from the impact forms a hot disk around the planet in the new equatorial plane. Over thousands to millions of years, this disk cools and condenses into moons. Some simulations produce results that match the Uranian system remarkably well. They tilt the planet to approximately the right angle. They produce a debris disk in the new equatorial plane that has roughly the right amount of mass to explain the 5 major moons. And they leave the planet's overall composition and bulk properties largely intact, consistent with what we observe. Other simulations are less successful. Some produce tilts that are too small, some eject too much mass from the system. Some produce disks that are too massive or too thin to form the right number of moons with the right sizes. The results depend sensitively on the impactor's mass, velocity, angle, and composition. Change any of these parameters by a modest amount and the outcome can shift significantly. This sensitivity is both a strength and a weakness of the giant impact model. It's a strength because it means the parameter space is rich. There are many combinations of impactor properties that can produce interesting results. Researchers can explore a wide range of scenarios and find plausible solutions. But it's also a weakness because the model doesn't uniquely predict what happened. There's no single definitive calculation that says this specific impactor with this specific mass hit Uranus at this specific speed, at this specific angle, at this specific time. The model tells us that a giant impact could explain the tilt, but it doesn't tell us exactly what form that impact took. This is where we need to step back and be honest about what science can and can't tell us. The giant impact hypothesis is the leading explanation for Uranus's tilt. It's consistent with the observations, it can reproduce the tilt angle, it can potentially explain the moon's orbits, it offers a pathway to understanding the lack of internal heat, and it's physically plausible given what we know about the violent conditions in the early solar system. But it's not confirmed. There's no smoking gun, no definitive piece of evidence that proves beyond doubt that a specific collision occurred at a specific time. The evidence is circumstantial, not direct. Compare this to the giant impact hypothesis for the formation of Earth's moon. In that case, we have lunar samples brought back by the Apollo astronauts. We can measure their isotopic ratios, we can compare them to Earth rocks, we can look for signatures of the extreme temperatures and pressures that a giant impact would produce. The evidence is detailed, specific, and testable. For Uranus, we have no such samples. We have no close-up data from an orbiter. We have one brief flyby from Voyager 2 nearly 4 decades ago, and ground-based and space telescope observations that provide useful but limited information. Without a dedicated mission to Uranus, some aspects of the impact hypothesis may remain untestable for decades. Despite these limitations, the giant impact model remains the strongest explanation available. And there's one more aspect of it worth discussing, because it connects directly to the broader story of how our solar system evolved. The timing of the impact matters enormously. If the collision happened very early, within the first 10 million years of the solar system's existence, then Uranus would have been still surrounded by the gas of the solar nebula. The nebula hadn't fully dispersed yet. In this case, the nebula gas could have helped damp out any disruption to the circumplanetary disk, allowing it to reform quickly in the new equatorial plane. The moons would then form from this re-established disk. This early timing also places the impact in the period when protoplanets were most abundant, making the collision more probable. If the collision happened later, during the period of giant planet instability described by the Nice model, roughly 3.9 to 4.1 billion years ago, then the impactor might have been a rogue protoplanet, dislodged from a previously stable orbit by the gravitational chaos of planetary migration. This is also plausible because the Nice model predicts that enormous amounts of material were scattered through the solar system during this unstable period. Planets were changing orbits. Large bodies were being flung in all directions. The probability of a collision between a stray protoplanet and one of the giant planets would have been significantly elevated. Recent work has even explored the possibility that the impactor itself was a captured satellite of Uranus, a large moon that was destabilized by gravitational perturbations from a passing planet during the instability period, and eventually collided with Uranus. This variant is elegant because it doesn't require a free-floating rogue body to hit Uranus by chance, but it requires very specific conditions, and the models are still being refined. What all these simulations and models ultimately tell us is that a giant impact is a physically realistic and scientifically robust explanation for Uranus's extreme tilt. The basic concept works. The physics checks out. The energies and angular momenta are in the right ballpark. Many important secondary observations, including the moon orbits and possibly the thermal structure, can be accounted for with careful tuning of the impact parameters. It's the best single explanation we have. But science doesn't work by just finding an explanation that works. It works by testing that explanation against alternatives. And as it turns out, there are alternatives to the giant impact model. Serious, well-developed alternatives proposed by respected planetary scientists and supported by their own sets of calculations and simulations. These alternatives don't involve a collision at all. They propose that Uranus was tilted slowly, gradually, through subtle gravitational processes acting over millions of years, processes that leave no crater, no debris disk, no sudden catastrophic event. Just the quiet, patient accumulation of tiny forces adding up over geological timescales to produce the same stunning result. These alternatives challenge the assumption that only something sudden and violent could produce a 98-degree tilt. They suggest that the universe is sometimes patient enough to achieve the same outcome through persistence that a collision achieves through brute force. And whether the truth turns out to be impact, resonance, or some combination of both, the story of Uranus's tilt remains one of the most fascinating detective stories in all of planetary science, because the clues are sparse, the evidence is circumstantial. The event, if it was a single event, happened more than 4 billion years ago. And the only way to solve the mystery is through the careful application of physics, mathematics, and computational simulation, working backward from the present state of a sideways planet to reconstruct the history that made it this way. So the giant impact model is strong. It may well be correct. But science demands that we test even strong ideas against alternatives. And over the past 2 decades, a completely different class of explanation has emerged. One that doesn't require a collision at all. One that replaces a single moment of violence with millions of years of patience. One that says you don't need to hit a planet to tip it over. You just need to push it gently, in exactly the right rhythm, for long enough. And that idea is just as physically real, just as mathematically rigorous, and just as capable of producing the 98 degrees we observe today. The question is which story the evidence ultimately supports. And that question remains wide open. There's something deeply satisfying about the giant impact hypothesis. A massive object slams into a young planet and knocks it sideways. The cause is dramatic. The effect is immediate. The connection between the two is intuitive. You can picture it in your mind. A protoplanet hurtling through the darkness, a catastrophic collision, a world wrenched onto its side in a matter of hours. It's the kind of explanation that feels right because it matches the scale of the phenomenon it's trying to explain. A 98-degree tilt seems like it demands a violent cause. But science doesn't always work that way. Sometimes the most dramatic outcomes are produced not by a single catastrophic event, but by the quiet, persistent accumulation of small forces acting over vast stretches of time. A river carves a canyon not through a single explosion of water, but through millions of years of steady flow. A mountain range rises not in a moment, but through the slow, relentless collision of tectonic plates over tens of millions of years. The Grand Canyon is one of the most dramatic geological features on Earth, and it was created by patience, not violence. Could the same principle apply to Uranus? Could a planet be tilted to 98 degrees, not by a single blow, but by the steady, patient application of gravitational forces acting over millions of years? A growing number of planetary scientists think the answer might be yes, and the mechanisms they've proposed are subtle, elegant, and in some ways even more fascinating than the brute force impact scenario. To understand these alternative explanations, you first need to understand a phenomenon called precession. Precession is what happens when a spinning object's axis of rotation slowly changes direction. You've probably seen this with a spinning top or a gyroscope. When a top starts to slow down, its axis doesn't stay perfectly vertical. Instead, the top of the axis traces out a slow circle, wobbling around a central point. The axis sweeps through a cone shape as it gradually shifts direction. That slow circular wobble is precession. Earth precesses. Right now, Earth's north pole points approximately toward Polaris, the North Star, but it doesn't stay pointed at Polaris forever. Earth's axis slowly traces out a cone, completing one full circle every 26,000 years. 12,000 years from now, Earth's North Pole will point toward Vega instead of Polaris. 12,000 years after that, it'll point back toward Polaris again. This precession is caused by the gravitational pull of the Sun and Moon on Earth's equatorial bulge. Earth isn't a perfect sphere. It bulges slightly at the equator because of its rotation. The Sun and Moon pull on this bulge, and because pull is slightly stronger on the near side of the bulge than on the far side, the result is a slow torque that causes the rotation axis to precess. Every planet precesses at a rate that depends on its spin, shape, distance from the Sun, and the gravitational environment, and that rate can change over time as orbits shift and moons migrate. Now, here's where it gets interesting. A planet's orbit also precesses, not the spin axis, but the orbit itself. The orbital plane slowly shifts direction over time due to gravitational perturbations from other planets. Jupiter's gravity tugs on Saturn's orbit, slowly changing its orientation. Saturn's gravity tugs on Uranus's orbit, doing the same thing. The result is that the orbital planes of all the planets are slowly wobbling, precessing, shifting in response to each other's gravitational influence. If a planet's spin axis precession rate happens to match its orbital precession rate, something remarkable can occur. The two motions become synchronized, locked together in what physicists call a resonance. Specifically, this is called a spin-orbit resonance. And when a spin-orbit resonance occurs, even very small gravitational forces can gradually drive the planet's axial tilt to extreme values. Think of it like pushing a child on a swing. If you push at random times, sometimes you'll add energy to the swing, and sometimes you'll subtract it. The net effect is small, but if you time your pushes to match the swing's natural rhythm, pushing at exactly the right moment in each cycle, even gentle pushes accumulate into enormous motion. The swing goes higher and higher with each perfectly timed push. That's resonance. A small force applied at exactly the right frequency can produce a large effect over time. In a spin-orbit resonance, the small force is the gravitational torque from the Sun and from other planets acting on the precessing spin axis. The matching frequency is the rate at which the orbital plane precesses. When these two rates coincide, the gravitational torque doesn't average out over time. Instead, it builds. Cycle after cycle, the torque pushes the spin axis in the same direction, gradually increasing the tilt. Given enough time, millions of years, the tilt can grow from a modest few degrees to tens of degrees, and under the right conditions, potentially much more. This mechanism was first explored in detail for Uranus by the French celestial mechanicians Gwenaël Bouet and Jacques Lascar in a landmark paper published in 2010. Their work showed that if Uranus once had a large satellite, a moon significantly more massive than any of its current moons, the gravitational interaction between this moon and Uranus could have increased the planet's spin axis precession rate enough to bring it into resonance with the precession of its orbit. Let me explain why the moon is so important in this scenario. Uranus's current moons are relatively small. The largest, Tyche Taini has a mass of only about 0.004% of Uranus's mass. That's tiny compared to, say, our moon, which has about 1.2% of Earth's mass. Because Uranus's moons are so small and so close to the planet, their gravitational effect on Uranus's precession rate is negligible. They don't speed it up or slow it down in any significant way. As a result, Uranus's current spin axis precession rate is far too slow to match the precession rate of its orbit. There's no resonance today. The two rates are completely mismatched. But what if things were different in the past? What if Uranus once had an additional moon, a large one, orbiting at a significant distance from the planet? A moon with, say, 1/100th of Uranus's mass, comparable to the mass ratio between our moon and Earth, orbiting at several 100,000 kilometers, could have exerted a substantial gravitational torque on Uranus's equatorial bulge. This torque would have sped up Uranus's precession rate, potentially bringing it into resonance with the orbital precession. Once the resonance was established, the mechanism would work like the swing analogy. Each precession cycle, the gravitational torque from the Sun and the other giant planets would push Uranus's axis a little further from vertical. Over millions of years, the tilt would steadily increase. The Moon, orbiting in Uranus's equatorial plane, would track the tilting axis, its orbit adjusting as the planet tilted, maintaining the resonance and allowing the tilt to continue growing. This is a fundamentally different picture from the giant impact model. There's no single catastrophic event, no explosion of debris, no superheated ejector. Instead, there's a slow, steady, almost imperceptible shift. Degree by degree, century by century, million of years by million of years, the planet's axis creeps sideways. If you were watching from outside the solar system, you'd barely notice anything happening on human timescales. The change would be so gradual that it would be invisible except over geological epochs. But the endpoint is the same. A planet tilted to extreme angles, lying on its side. The beauty of this mechanism is that it naturally explains the moon's equatorial orbits. In the resonance scenario, the moons tilt with the planet the entire time. They're orbiting in the equatorial plane throughout the process. As the planet's axis slowly shifts, the equatorial plane shifts with it, and the moons follow along. There's no moment of sudden disruption, no need to destroy an existing moon system and rebuild it from a debris disk. The moons simply ride the tilting axis like passengers on a slowly rotating platform. But here's the catch. The original Bouet and Lascar model requires a large moon that doesn't exist today. None of Uranus's 28 known moons is massive enough to produce the necessary precession rate. If the resonance mechanism is correct, the large moon that drove the tilt must have been lost at some point, after the tilt reached its final value. And losing a large moon is not a simple thing. Moons don't just vanish. So what could have happened to this hypothetical moon? There are several possibilities, and each one has been explored in the scientific literature. The most commonly proposed fate is that the moon became orbitally unstable, and was either ejected from the Uranian system entirely, or collided with the planet. If the resonance drove Uranus's tilt past a certain threshold, the gravitational dynamics of the system could have become chaotic. The large moon's orbit might have been destabilized by interactions with the other moons, or by the changing geometry of the gravitational field as the tilt increased. Once destabilized, the moon could have been flung outward, escaping Uranus's gravity and drifting away into a heliocentric orbit around the Sun, eventually being absorbed by another planet or ejected from the solar system entirely. Or it could have spiraled inward and crashed into Uranus, its mass absorbed into the planet's bulk, leaving no trace except the tilt it helped create. This is admittedly speculative. We have no direct evidence that such a moon ever existed. We can't point to a crater or a chemical signature that proves a large moon once orbited Uranus and was then destroyed or lost. The hypothesis is based entirely on dynamical modeling. It works in the mathematics. The equations produce the right outcome, but there's no physical artifact we can examine to confirm it. This is one of the main criticisms of the resonance model. It requires a large, now missing moon, and there's no independent evidence for that moon's existence. However, the loss of a large satellite is not as implausible as it might sound. The early solar system was chaotic enough that losing moons was probably not uncommon. Neptune's largest moon, Triton, orbits the planet in the wrong direction, retrograde, strongly suggesting it was captured from the Kuiper belt rather than born around Neptune. When Triton was captured, any pre-existing prograde moons would have been gravitationally disrupted, flung out, or destroyed. Neptune's original moon system was likely wiped out and replaced. If Neptune can lose its entire original moon system through the capture of a single, large retrograde body, it's not unreasonable to think that Uranus could have lost a single large moon through the gravitational perturbations associated with planetary migration and the instability period. The Nice model predicts that the giant planet's orbits change dramatically during this era. Uranus and Neptune may have even swapped positions, with Uranus originally forming closer to the Sun than Neptune, and then migrating outward during the instability. These orbital changes would have subjected every moon system to intense gravitational stress. Losing a moon during this period is plausible, even expected. In 2020, researchers Rogozinski and Hamilton published a study that expanded on the resonance model by exploring a wider range of parameters. They investigated whether the resonance could work with a moon smaller than the one originally proposed by Bouet and Laskar. They found that under certain conditions, particularly if the resonance was established early when the circumplanetary disk was still present and could contribute additional mass to the effective gravitational torque, a somewhat smaller moon might suffice. They also found that the resonance could potentially tilt Uranus even past 90 degrees, producing retrograde rotation, which would then appear as a tilt of greater than 90 degrees. Recall that Uranus's measured tilt of 97.8 degrees technically means it rotates slightly retrograde. A tilt of exactly 90 degrees would mean the axis is perfectly horizontal. 97.8 degrees means it's actually tilted just past horizontal, so the planet is spinning very slightly backward relative to its orbit. The resonance model can produce this behavior naturally if the tilt overshoots 90 degrees before the resonance is broken. There's yet another variant of the gradual tilting hypothesis that doesn't require a lost moon at all. Instead of relying on a satellite to speed up Uranus's precession, some researchers have proposed that the early solar nebula itself could have provided the necessary torque. When the giant planets were still young, within the first few million years of the solar system's existence, they were still embedded in the remnants of the gas disk from which the solar system formed. This disk, though thinning, still contained significant mass. Gravitational interactions between the planet and the disk, particularly if the disk was warped or tilted relative to the planet's orbital plane, could have exerted a torque on the planet's spin axis. If the disk torque happened to push Uranus's precession rate into resonance with its orbital precession at the right time, the same amplification mechanism would kick in. The tilt would grow gradually, driven by the resonance, with the disk providing the extra torque needed to make the rates match. Once the disk dissipated, the resonance would break and the tilt would stop growing. The planet would be left at whatever angle it had reached when the disk vanished. This scenario is elegant because it doesn't require any hypothetical lost moon. It uses a component of the early solar system, the gas disk, that we know existed. The disk was real. It was massive. It exerted gravitational forces on the planets. The question is whether those forces were strong enough and oriented correctly to drive the necessary precession resonance. The answer, according to some models, is maybe. The parameters have to be just right. The disk has to have the right mass, the right geometry, and the right timing of dispersal. Not all disk models produce the resonance, but some do. There's also a broader class of models that involve gravitational interactions between the giant planets themselves during the migration and instability period. During the Nice model instability, the giant planets were undergoing close gravitational encounters. Jupiter and Saturn were migrating in opposite directions. Uranus and Neptune were being scattered outward. During this chaos, the gravitational influence of Jupiter and Saturn on Uranus would have been much stronger than it is today, because the planets were closer together and their orbits were more eccentric. Some researchers have explored whether these enhanced gravitational interactions could have directly tilted Uranus's axis. The idea is that during a particularly close encounter between Uranus and another giant planet, the tidal forces and gravitational torques could have been strong enough to shift Uranus's spin axis significantly. Not by 98 degrees in a single flyby, necessarily, but by enough to start the process or to work in conjunction with other mechanisms. For example, imagine a scenario where Uranus migrates outward through the solar system during the instability. Along the way, it passes through a region where its orbital precession rate temporarily matches its spin precession rate, establishing a spin-orbit resonance. The resonance tilts Uranus to, say, 40 or 50 degrees over a few million years. Then the resonance breaks as Uranus's orbit changes further. But later, a close gravitational encounter with Neptune or a large scattered body adds another 20 or 30 degrees to the tilt. And finally, a modest impact from a body of perhaps half an Earth mass adds the remaining amount. The total reaches 98 degrees, but no single mechanism is responsible. It's a combination of resonance, gravitational encounter, and impact, all working together during the chaotic early solar system. This combined scenario is increasingly favored by some researchers because it relaxes the constraints on each individual mechanism. The impact doesn't need to be as large, the resonance doesn't need to last as long, the gravitational encounters don't need to be as close. Each mechanism contributes a portion of the tilt, and together they reach the extreme value we observe. But there's a philosophical point here worth noting. As we add more mechanisms, the hypothesis becomes harder to test. A single giant impact makes specific predictions you can simulate and compare to observations. A combined scenario has more free parameters and more knobs to turn. In science, a hypothesis that can explain everything explains nothing. The best explanations are specific enough to be wrong if the data don't match. This is why the debate between the impact model and the resonance model remains active and unresolved. Both are physically plausible, both can produce the observed tilt, both have strengths and weaknesses, and neither has been definitively confirmed or ruled out. Let's examine one more piece of evidence that bears on this question, because it's a piece that doesn't get discussed enough, and it tells us something important about the limits of our current knowledge. The internal structure of Uranus is poorly understood. We know from Voyager 2's measurements that Uranus has a magnetic field, and as we'll discuss in detail later, that magnetic field is bizarre. It's tilted about 59 degrees from the rotation axis and offset from the planet's center. This suggests that the field is generated not in a deep iron core like Earth's magnetic field, but in a shallower layer of electrically conducting fluid, probably a mixture of water, ammonia, and methane at extreme pressures, where these substances behave as electrical conductors. The structure and geometry of this magnetic field are clues about what happened to Uranus's interior. A giant impact would have deposited enormous amounts of energy deep inside the planet, potentially disrupting the internal structure and creating compositional gradients that persist to this day. A gradual tilting through resonance, by contrast, would have left the internal structure largely undisturbed. The planet would have tilted slowly, gently, without the violent mixing and heating that an impact would produce. If we could measure Uranus's internal structure precisely, if we could map its gravitational field with enough detail to determine how mass is distributed inside the planet, we might be able to distinguish between these scenarios. A giant impact would likely produce a different internal mass distribution than a gradual resonance-driven tilt. The impact might create a partially mixed interior with composition gradients that wouldn't exist in the resonance scenario. The resonance model might leave Uranus's interior more uniform, more consistent with what you'd expect from a planet that formed normally and was never violently disrupted. This is one of the strongest arguments for sending a dedicated spacecraft to Uranus. A Uranus orbiter, equipped with instruments to map the planet's gravitational field, magnetic field, atmospheric composition, and internal heat flow, could potentially provide the data needed to distinguish between the impact and resonance models. Several mission concepts have been proposed. In 2022, the United States National Academies of Sciences published a decadal survey, a once-per-decade report that sets priorities for planetary science, and the survey recommended a Uranus orbiter and probe as the highest priority flagship mission for the coming decade. If funded and built, such a mission could launch in the early 2030s and arrive at Uranus in the mid-2040s. Until such a mission flies, we're limited to the data we have. Voyager 2's brief flyby. ground-based telescopic observations, space telescope observations from Hubble and the James Webb Space Telescope, and computational simulations that model the various scenarios and compare their predictions to these observations. It's not a lot to work with, but it's enough to establish that both the giant impact model and the resonance model are serious, viable explanations for one of the solar system's most striking features. And it's worth stepping back and appreciating what this debate represents in the broader context of planetary science. When we look at Uranus and see its 98-degree tilt, we're looking at a piece of evidence, a clue about the solar system's violent and complex history. The fact that we can't yet definitively determine whether the tilt was caused by a single catastrophic impact or by a slow, resonance-driven process isn't a failure of science. It's a reflection of how difficult it is to reconstruct events that happened over 4 billion years ago from limited data. The clues are subtle, the physics is complicated, and the answer may turn out to be a combination of mechanisms working together in ways we haven't fully modeled yet. What we can say with confidence is that Uranus's tilt did not arise from the normal process of planet formation. No standard model of accretion from the solar nebula produces a tilt anywhere near 98 degrees. Something extra happened, something beyond the normal physics of disk accretion and gravitational settling. Whether that something was a single violent collision, a slow gravitational resonance amplified over millions of years, or a combination of both, it tells us that the solar system's history was far more dynamic, far more chaotic, and far more interesting than the calm, orderly present-day arrangement of planets would suggest. The phrase, flipped by force, in our title is deliberately broad. Force doesn't have to mean a single blow. Force can be gravitational, force can be tidal, force can be the accumulated effect of millions of gentle pushes, timed perfectly through resonance. All of these are forces in the physical sense. All of them involve the transfer of angular momentum, and all of them are capable, under the right conditions, of producing one of the strangest orientations in the entire solar system. Uranus stands as a reminder that planets are not static, finished objects. They're dynamic systems shaped by their histories, modified by the forces acting on them, carrying the scars and signatures of events that happened billions of years ago. The tilt is not just a number in a table, it's a story, a compressed record of dynamical interactions that we're still learning to read. And the fact that we haven't finished hearing it yet, that the debate between impact and resonance remains open, is one of the things that makes this particular story so compelling. But here's what's remarkable. We've been talking about the cause of the tilt, the event or process that produced it. And that's a fascinating question. But there's another question that's equally important and far easier to investigate with the tools we already have. What does the tilt actually do to Uranus right now? Because a planet tilted 98 degrees doesn't just look different on a diagram, it behaves differently. It experiences seasons no other planet experiences. It generates a magnetic field unlike anything else in the solar system. Its atmosphere responds to sunlight in ways that confounded scientists the first time they saw it up close. The tilt isn't just a mystery about the past, it's a living, ongoing, observable phenomenon that shapes everything about this world today. And understanding those consequences turns out to be just as revealing as understanding the cause, whether the truth turns out to be a single titanic collision, a patient resonance amplified across epochs, or a complex interplay of both. One thing is certain. The answer will reshape our understanding of how planetary systems are assembled, how they evolve, and how even the most fundamental properties of a world, the direction it faces as it spins, can be transformed by the forces at work in the cosmos. Uranus didn't choose to be sideways. Something made it that way. And the quest to identify that something is one of the great ongoing detective stories in the exploration of our solar system. So far, we've explored how extreme Uranus's tilt is, why it demands a special explanation, and what physical processes might have caused it. But we haven't yet talked about what happens when you actually live with a 98-degree tilt. What does it mean for a planet to be sideways? Not in the abstract, not as a number in a textbook, but in physical, observable, measurable reality. What does Uranus actually experience as it rolls around the sun on its side? Because the consequences are extraordinary. The tilt doesn't just make Uranus look strange. It makes Uranus behave differently from every other planet in the solar system. Its seasons, its magnetic field, its atmospheric circulation, and even its oddly bland appearance are all shaped by the fact that this planet's rotation axis points almost directly at the sun for long stretches of its orbit. The tilt isn't just a historical curiosity, it's the defining feature of everything that happens on and around Uranus today. Let's start with seasons, because this is where the tilt has its most dramatic and intuitive effect. On Earth, seasons are produced by our 23.5-degree tilt. When the northern hemisphere tilts toward the sun, it's summer in the north and winter in the south. 6 months later, the geometry reverses. The tilt is moderate, so the seasonal variation is moderate. Summer days are longer and warmer, winter days are shorter and cooler. But no location on Earth outside the polar circles experiences continuous sunlight or continuous darkness for more than a day. Even at the Arctic Circle, the longest period of midnight sun is roughly a few weeks around the summer solstice. Uranus is nothing like this. Uranus takes about 84 Earth years to complete one orbit around the sun. Its axis is tilted 97.8 degrees. This means that at the solstices, when one pole is pointed most directly at the sun, that pole receives nearly continuous sunlight, while the opposite pole sits in nearly total darkness. And these solstices don't last a few weeks. They last for roughly 21 Earth years. Think about what that means. If you were somehow floating in the atmosphere above Uranus's north pole during the northern summer solstice, you would see the sun hanging overhead, never setting, for more than 2 decades. The sun would trace slow, lazy circles in the sky, spiraling gradually lower toward the horizon as the years passed and the planet moved along its orbit, but never dipping below the horizon for roughly 21 years. Meanwhile, the South Pole would be plunged into darkness for that same 21-year stretch. No sunlight at all. Just cold, black sky for more than 2 decades. Then, about 21 years later, Uranus reaches its equinox. The sun shines on the equator, and both hemispheres receive roughly equal illumination, with a normal day-night cycle repeating every 17 hours. But this relatively normal period doesn't last. Within a few years, the opposite pole begins its long turn toward the sun, while the other starts its descent into 2 decades of darkness. The energy distribution this creates is profoundly unusual. During the solstice, the pole facing the sun receives more solar energy per unit area than the equator does. This is the opposite of what happens on most planets. On Earth, Mars, Jupiter, and Neptune, the equator always receives the most solar energy because it always faces the sun most directly. The poles receive the least because sunlight hits them at a shallow angle. But on Uranus at solstice, the geometry is inverted. The pole aimed at the sun is receiving direct overhead sunlight, while the equator is in a perpetual twilight, with the sun hugging the horizon and delivering its energy at extreme angles. You might expect this extreme, lopsided heating to produce dramatic weather. You'd expect massive temperature differences between the sunlit pole and the dark pole. You'd expect powerful winds rushing from the warm hemisphere to the cold one. You'd expect towering storm systems and swirling vortices driven by the enormous thermal gradients. And on some level, those expectations are correct. The temperature differences are real, but the atmosphere of Uranus doesn't respond the way you might intuitively predict. And that mismatch between expectation and observation is one of the most puzzling aspects of this planet. When Voyager 2 flew past Uranus in January of 1986, it arrived during the southern summer solstice. The South Pole was pointed almost directly at the sun. Scientists expected to see a dynamic, active atmosphere, maybe not as dramatic as Jupiter's bands and storms, but something. What they saw instead was startling. Almost nothing. The atmosphere appeared nearly featureless. A pale blue-green sphere with virtually no visible cloud bands, no large storms, no obvious structure of any kind. Compared to Jupiter's swirling belts and zones, and its great red spot, compared to Saturn's banded atmosphere and its hexagonal polar vortex, Uranus looked blank, inert, boring. This was deeply confusing. How could a planet with such extreme seasonal forcing, with one pole baking in continuous sunlight while the other freezes in continuous darkness, have such a bland atmosphere? Where were the storms? Where were the temperature-driven winds? Where was the visible response to this bizarre heating pattern? Part of the answer turns out to be connected to the very mystery we've been exploring. Uranus radiates almost no excess internal heat. Remember, Jupiter, Saturn, and Neptune all radiate significantly more energy than they receive from the Sun. This internal heat drives convection in their atmospheres, powering the bands, storms, and vortices we observe. Jupiter's internal heat is so strong that it dominates the planet's atmospheric dynamics. Even Neptune, which is farther from the Sun and receives less solar energy than Uranus, has a more active atmosphere because it radiates about 2.6 times as much energy as it absorbs from the Sun. Neptune has the fastest winds in the solar system, reaching up to 1,200 miles per hour. Driven largely by internal heat, flowing upward through the atmosphere and generating powerful convective activity, Uranus doesn't have this engine. Whatever happened to its interior, whether a giant impact created a thermal boundary layer that traps heat inside, or whether some other process is at work, the result is that Uranus's atmosphere lacks the internal energy source that drives atmospheric activity on the other giant planets. Without internal heat rising through the atmosphere and creating turbulent convection cells, the atmosphere tends to be more stable, more layered, more sluggish. The solar energy hitting the sunlit pole is real, but it's relatively weak at Uranus's distance of about 19.2 astronomical units from the Sun. Uranus receives only about 1/400th as much solar energy per square meter as Earth does. That's not much to work with, even concentrated on one pole for 21 years. However, the story isn't quite as simple as Uranus having a dead atmosphere. Since the Voyager 2 flyby, ground-based telescopes and space telescopes have revealed more atmospheric activity than Voyager saw. As Uranus approached its 2007 equinox, when the sun was shining on its equator and both hemispheres were being heated more equally. Astronomers observed bright cloud features, storm systems, and atmospheric bands that hadn't been visible during the Voyager flyby. The Hubble Space Telescope captured images showing distinct cloud bands and bright high-altitude cloud features. The atmosphere was waking up. This makes physical sense. During the equinox, the temperature gradient between the equator and the poles shifts. The equator becomes the warmest region again, and the poles begin cooling. This transition in the heating geometry could trigger atmospheric instabilities, creating the storms and cloud features that weren't present during the solstice when the heating pattern was more pole-dominated. The atmosphere of Uranus appears to be seasonal in a way that no other planet's atmosphere is. Its appearance changes not over weeks or months, but over decades, tracking the planet's 84-year orbit and the slowly shifting geometry of how sunlight falls on its tilted surface. More recently, the James Webb Space Telescope has observed Uranus in infrared wavelengths that penetrate deeper into the atmosphere than visible light. These observations have revealed more structure than was apparent in visible light images. There are hints of deeper circulation patterns, temperature variations at different atmospheric levels, and compositional differences between different latitudes. Uranus isn't truly featureless. It's just subtler than the other giant planets, its atmospheric activity muted by the absence of internal heat, but still present and still driven by the extreme seasonal forcing that the tilt creates. Now let's talk about Uranus's magnetic field, because this is where the tilt story becomes even stranger. Every planet with a significant magnetic field generates that field through a process called a dynamo. Deep inside the planet, electrically conducting fluid moves through convection, flowing in patterns driven by heat escaping from the interior. This moving conductor generates electric currents, and those electric currents produce a magnetic field. On Earth, the conducting fluid is molten iron in the outer core. On Jupiter and Saturn, it's metallic hydrogen. Hydrogen compressed to such extreme pressures that it behaves as a liquid metal. The magnetic fields of Earth, Jupiter, and Saturn all have a basic dipole structure, meaning they look roughly like the field of a bar magnet, with a north pole and a south pole. And in all three cases, the magnetic dipole is roughly aligned with the rotation axis. Earth's magnetic field is tilted about 11 degrees from the rotation axis. Jupiter's is tilted about 10 degrees. Saturn's is almost perfectly aligned, tilted less than 1 degree. Uranus breaks this pattern completely. Uranus's magnetic field is tilted about 59 degrees from the planet's rotation axis. That's enormous. It means the magnetic poles are nowhere near the geographic poles. On Earth, your compass needle points approximately toward the geographic North Pole because the magnetic pole and the geographic pole are close together. On Uranus, a compass would point in a direction wildly different from the geographic pole. The magnetic equator of Uranus passes close to the geographic poles. It's as if someone took Earth's magnetic field and rotated it sideways relative to the planet's spin. But it gets even more unusual. Uranus's magnetic field is not centered on the planet. It's offset from the center by about 1/3 of the planet's radius. Imagine the magnetic field being generated not at the core of the planet but off to one side, deep in the interior, but not at the center. This produces a magnetic field that's asymmetric, stronger on one side of the planet than the other, and with a complex multipolar structure that looks very different from the simple dipole fields of Earth, Jupiter, and Saturn. What could produce such a bizarre magnetic field? The answer likely lies in Uranus's internal structure, which in turn may be connected to whatever event caused the tilt. On Earth, the magnetic field is generated deep in the core, at the very center of the planet. The core is made of dense iron, and the symmetry of the core combined with the planet's rotation produces a relatively clean, symmetric dipole field. On Uranus, the field appears to be generated not in a deep central core, but in a shallower layer, perhaps in a shell of electrically conducting fluid made of water, ammonia, and methane at extreme pressures. At the temperatures and pressures found deep inside Uranus, these substances behave as ionic fluids, capable of conducting electricity and generating magnetic fields through dynamo action. If the dynamo operates in a shallow shell rather than a deep core, the resulting magnetic field would naturally be more complex and less dipolar. The offset and tilt could be a consequence of the geometry of this conducting layer. And here's the connection to the tilt. If a giant impact disrupted Uranus's interior, partially mixing the layers and creating compositional gradients that don't exist in the other giant planets, the location and geometry of the conducting layer could be very different from what you'd find in an undisturbed planet. The impact might have created the conditions that produce the offset, tilted magnetic field we observe. Neptune, interestingly, has a similarly weird magnetic field. Neptune's magnetic dipole is tilted about 47 degrees from its rotation axis, and is also offset from the planet's center. This is striking because Neptune doesn't share Uranus's extreme axial tilt. Neptune's axis is tilted only about 28 degrees, well within the normal range. So whatever produces the weird magnetic fields of Uranus and Neptune, it's not simply the axial tilt itself. It might be something about the internal structure of ice giants in general, perhaps a shallow dynamo mechanism that arises naturally in planets made primarily of water, ammonia, and methane rather than metallic hydrogen. This raises an important point. Not every strange feature of Uranus is necessarily caused by the tilt event. Some features may be intrinsic to being an ice giant. Separating the effects of the tilt from the effects of being a particular type of planet is one of the key challenges in understanding Uranus, and it's another reason why a dedicated orbital mission would be so valuable. By comparing Uranus and Neptune in detail, by mapping their gravitational fields, magnetic fields, atmospheric compositions, and internal structures, scientists could begin to disentangle which features are universal to ice giants and which are unique consequences of Uranus's particular history. The magnetic field's bizarre orientation has another dramatic effect that's directly connected to the tilt. A planet's magnetosphere, the bubble of magnetic influence that surrounds the planet and deflects the solar wind, is shaped by the interaction between the planet's magnetic field and the stream of charged particles flowing out from the sun. For most planets, the magnetosphere is roughly aligned with the rotation axis and roughly symmetric. The solar wind hits the magnetosphere head-on, compresses it on the sunward side, and stretches it out into a long magnetotail on the opposite side. The geometry is straightforward. For Uranus, the geometry is anything but straightforward. Because the magnetic axis is tilted 59 degrees from the rotation axis, and the rotation axis is tilted 98 degrees from the orbital plane, the magnetic axis tumbles wildly relative to the solar wind as the planet rotates. Every 17 hours as Uranus completes one rotation, the magnetic poles swing through enormous arcs. Sometimes a magnetic pole points toward the sun, sometimes it points away. The magnetosphere is constantly being twisted, distorted, and reconfigured as the planet spins. The result is a magnetosphere that's unlike anything else in the solar system. It's been described as a corkscrew or a spinning top that wobbles unpredictably. The magnetotail, which on most planets streams away from the sun in a relatively straight line, is twisted into a helical shape behind Uranus, spiraling outward like a corkscrew as the planet rotates. Charged particles trapped in the magnetic field follow complex, chaotic paths rather than the relatively orderly trajectories they follow in Earth's or Jupiter's magnetospheres. Voyager 2 detected this bizarre magnetosphere during its flyby and measured its properties. The data confirmed that the magnetic field was wildly offset and tilted, and that the magnetosphere was being continuously deformed by the mismatch between the magnetic axis, the rotation axis, and the direction of the solar wind. Understanding the detailed physics of this interaction is still an active area of research, and it represents one of the most complex problems in planetary magnetophysics. Let's bring all of this together and think about what Uranus tells us about the broader story of planetary systems. Because Uranus isn't just one weird planet. It's a window into the processes that shape all planets everywhere. The fact that Uranus's tilt exists at all tells us that the formation of planetary systems is not a smooth, orderly process. It's violent. It's chaotic. It involves collisions, gravitational instabilities, orbital migrations, and resonances that can radically transform a planet long after it initially forms. The tidy, neat solar system we see today, with planets orbiting in roughly circular paths at roughly regular intervals, is the end product of billions of years of evolution. The early solar system was a very different place, a turbulent environment where the architecture of the planetary system was still being determined. Uranus's tilt is one of the most visible scars from that era. It's a reminder that the calm present conceals a violent past, and it's not unique. Every planet carries signatures of its history. Earth's oversized moon is the legacy of the impact. Mars's hemispheric dichotomy may record an ancient giant collision. Mercury's enormous iron core may be the remnant of a mantle-stripping impact. Saturn's rings may be the debris from a destroyed moon. The solar system is littered with evidence of catastrophic events that reshaped worlds billions of years ago. But Uranus's tilt is arguably the most dramatic of all these signatures. Other planets show evidence of individual impacts or specific events. Uranus shows evidence of something that fundamentally changed how the planet interacts with the sun, how its seasons work, how its magnetic field behaves, and how its atmosphere circulates. The tilt didn't just leave a scar, it redefined the planet's relationship with the rest of the solar system. As we discover more planetary systems around other stars, we're finding that extreme obliquities, planets with large axial tilts, may not be as unusual as we once assumed. Our solar system contains one dramatically tilted planet out of 8, but some theoretical models of planetary formation suggest that large tilts could be common in systems where giant planets migrate or undergo dynamical instabilities. If giant impacts and spin-orbit resonances are as common in other systems as they appear to have been in ours, then sideways planets might be scattered throughout the galaxy. Some exoplanets may be tilted even more extremely than Uranus, rolling along their orbits with their poles pointed directly at their stars. experiencing seasons so extreme they make Uranus look moderate by comparison. We can't yet measure the axial tilts of exoplanets directly. The technology doesn't exist, but future observations, particularly of exoplanets' atmospheric variability over the course of their orbits, might allow us to infer their tilts from how their brightness and spectral features change with time. A planet with an extreme tilt would show very different atmospheric signatures at different points in its orbit, as the heating pattern shifted from pole-dominated to equator-dominated. Detecting these signatures would be extraordinarily difficult with current instruments, but it's not impossible in principle, and future telescopes may bring it within reach. Understanding Uranus is therefore not just about understanding one planet. It's about understanding a universal process that operates in planetary systems throughout the cosmos. Giant impacts happen wherever planets form. Gravitational resonances occur wherever multiple massive bodies orbit the same star. The mechanisms that tilted Uranus are not unique to our solar system. They're general physical processes that operate according to the same laws of gravity and angular momentum that govern everything in the universe. Uranus just happens to be the most dramatic example of their consequences that we can study up close. And that's ultimately what makes Uranus's tilt so scientifically valuable. It's not a trivial oddity. It's not a cosmic footnote. It's a direct, observable record of the kinds of extreme events that shape planetary systems. Every measurement we make of Uranus, every observation of its atmosphere, its magnetic field, its moons, its rings, its internal heat, is a potential clue about what happened 4 billion years ago, and about the general processes that build and reshape planets everywhere. The planet sits out there right now, about 2.9 billion kilometers from the Sun, rolling along its orbit, tilted at 97.8 degrees. One pole is slowly emerging from decades of darkness. The other is beginning its long descent into night. The magnetic field tumbles wildly as the planet spins, twisting the magnetosphere into corkscrews. The moons orbit faithfully in the tilted equatorial plane, tracing paths that are sideways relative to the rest of the solar system. The rings circle the planet in the same tilted plane, thin and dark and nearly invisible, discovered only because they block the light of a distant star at just the right moment. Everything about this world testifies to an extraordinary history. The tilt itself, the orderly moons orbiting in the wrong plane, the offset, misaligned magnetic field, the missing internal heat, the seasonally variable atmosphere. Each of these features is a sentence in a story written 4 billion years ago in a language of physics that we're still learning to read fluently. And what makes this even more exciting is that the next phase of this investigation is within reach. The Uranus orbiter and probe mission we discussed earlier, if it's built and launched, could finally provide the measurements needed to distinguish between competing hypotheses and answer the question that has haunted planetary science for decades. What exactly happened to Uranus? Was it a single titanic collision with a protoplanet the size of Earth? Was it a slow, patient gravitational resonance amplified over millions of years by a moon that no longer exists? Was it some combination of both? Or was it something we haven't thought of yet, hidden in the data waiting to be discovered? We don't know yet. And that's the honest answer. But that's what makes this one of the great open questions in planetary science. The mystery isn't solved. The clues are still being gathered. And the answer, when it finally comes, will tell us something profound, not just about one sideways planet, but about the nature of planetary formation itself, and the deep, sometimes hidden forces that shape everything in the cosmos. Uranus wasn't born sideways. Something made it that way. Something powerful. Something that left its fingerprints on every aspect of the planet, from its poles to its core to its outermost ring. And the search for what that something was is one of the most compelling, most consequential, and most beautifully unresolved investigations in our exploration of the solar system. The next time you look at the night sky and think about the planets, remember that one of them is rolling along out there in the darkness, tilted almost completely on its side, carrying 4 billion years of history in its orientation. It can't tell us its story in words, but it tells us in physics, in the angle of its spin, in the paths of its moons, in the shape of its magnetic field, in the silence of its missing heat. These are the words of Uranus's story, written in the universal language of nature. And we're getting closer to hearing them every year.